another Thursday seminar, and I must share a couple of facts about this seminar today. I'm sitting right now at the IEEE NFV SDN conference on a side room. It has been a great week of contents in the field of networking, where it's the main focus of my research. I'm also glad to have today with you, which, by the way, is the last seminar of this semester. Next year, we'll be back with lots of great talks of hopefully so many great IEEE distinguished lecturers like we have today. And today is a topic also, like I was saying, about networking. Okay, how the science of complex systems can inspire future autonomous networkers. The talk is by Nicola Marchetti. He's a professor in Trinity College Dublin in Ireland. And we were just catching up a little bit, and there are great connections that I'm very happy to follow up. As always, here is the great biography. You have the contact information, all the Google Scholar pointers to the publications. And so, Nicola, thanks again for being here. And I look forward to catch up with you more, to bring you some of the questions from the audience that will follow us from YouTube, and from the students who have done their homework and that have prepared some nice questions for you.
Very good.
Okay. Great. I will stop sharing over here because Meet doesn't like to stream two of us at the same time. You can now share your screen.
Yes, I'm going to do that, and you should be able to see my.
Yes.
I'm just going to swap. Yep, that should do it.
Okay, perfect, excellent. So, talk to you in around 40 minutes, and thanks again for being here.
Yeah, thanks, Christian. So I can start, yeah?
Yes, please.
Yeah, thanks, Christian, for the kind invitation, and for all the people of Unicamp, you know, and that joined this seminar, and whoever else, right, is joining through YouTube. So it's a great pleasure to talk about some of the research I've been doing with my team here in Trinity College in Dublin, in Ireland, and yeah, and essentially how this might give you some ideas for, you know, future open problems, hopefully. So yeah, I will not spend much time to tell you about ComSoc, because you know all about it. It's one of the largest societies in IEEE, right? And definitely the to-go place if you want to know more about the communication engineering trends and networks, right, these days. So just maybe a couple of words about my institution here in Ireland. So it's one of the oldest universities in the English-speaking world. So we were founded more than 4 centuries ago. So we, among our alumni, we can count 4 Nobel Prizes, including 2 in sciences, so 1 in physics, 1 in medicine. We have about 20,000 students, and among our alumni, we also have famous writers like Oscar Wilde, Jonathan Swift, and Bram Stoker, who wrote Dracula. So you probably you definitely know the novel. And just a couple of pictures of the campus, which is very beautiful. So we have, you know, very traditional buildings and a lot of history. So if you ever happen to be in Dublin, it's definitely worth you know, worth your time, and you can't miss it because we are really at the heart of the city. So most of the campuses normally of the universities right around the world are a bit outside the city for good reasons, but historically Trinity College actually was born in the middle of Dublin, so it's really at the heart of the city. So if you want to visit Dublin, it's easy to visit our college. Right, just maybe a couple of words of introduction before I go into the technical topic. So the research we did in this domain relies on ideas that actually are not really originally from networks. So we are talking about ideas that come from 3 fields mostly, so theoretical computer science, physics, and biology. And the proof is a couple of Nobel Prizes in recent years, so namely in 2020 and 2021, were awarded to physicists that actually are working in complex systems. So what are these complex systems? So essentially they are a collection of simple entities that take local actions and communicate only with their neighbors. And you expect the overall system, comprising all of these local agents, to actually perform well. So you're not allowed to do a central widespread optimization. You can only take local actions via simple actions and simple interactions. But you can actually, if you do it right, you can scale up the behavior so that the performance is satisfactory. And a good example is nature, right? So if you have, if you consider flocks of birds, a school of fishes, colonies of ants, and so on and so forth, any ecosystem would really work like that. So why did we look at this, kind of alien topic, and why do we think it's useful for communication networks? Essentially, the most of the communication networks we are discussing for the future are actually very large in scale. They are supposed to be distributed. So if you think of things like vehicular networks, massive IoT, ultra-dense cellular deployments, you basically have this situation where you have a lot of devices. You can't really optimize things centrally because of the scale and because it would take too much time. You might not have all the data you need. So the idea is that you let the agents or these individual entities figure out what to do. Another thing that resembles what happens in complex systems in nature and in physics is actually they're very dynamical. So there is a high variability in time, but also in other domains, so like frequency and space. And these are systems that are normally between something completely regular and something completely random. So it's, in a sense, it makes sense to predict because it's possible and it's not useless. So you can think, for example, of recent developments in machine learning as a good complement to the research we've been doing here. So I will have a bit of that toward the end of the presentation. Right, so in the end, we want things that are potentially very scalable. They must be distributed. And we are going to take some inspiration from self-organization principles that are found abundantly in nature. Right, so there are three main topics in this presentation. So one is about information. So how do we define information in these complex communication systems? The second one is about network, in the sense of what are the topology aspects that are more important. And the final one is dynamics. So it's essentially time, right? How things evolve in time. And then we'll try to wrap up with some final considerations. So one work we did actually a few years ago was to try and see if we can capture the functions that a network perform via some graphs. So we kind of abstract the functionalities of the graph, of the network into a graph that is actually easy to understand, easier at least than the underlying real network. And here, for example, we took a couple of clustering algorithms in wireless sensor networks and try to see how different nodes, different parts of the network interact. So what we call the functional topology has to do with the participation of, say, devices or anyway functions in the network into basically the working of the system. So in this case, it's about creating clusters so you can actually reduce overhead and reduce energy consumption, essentially. So here we took two algorithms. One is called Leech, which tends to create dense clusters, okay, because that's what the algorithm aims to do. And the other one is ACC, which tends to create spread out topologies. So there are two very different algorithms, and we try to see if we can understand actually what's going on in terms of information processing here. So in the case of Leech, what we noticed is actually that, well, first of all, let's say you can compute what we call functional complexity, which is a measure of the nonlinearity of a system. So if you look at this first equation, it's essentially telling you how scaling up a system has impact on the uncertainty of interaction. So if you see the straight line, is what a linear system, a normal system that is not complex, would do. So if you increase the size of the system, you get actually an average amount of information that goes proportionally. But a complex system does something else. So you basically have, in a sense, non-trivial ways of interacting of the nodes in a topology. So you see actually a curve that is higher than that. So you basically exchange more information on average. Why? Because essentially it's less predictable which nodes are involved. Okay, it can be basically any node in your neighborhood. Why a linear system would actually be much more predictable. So it turns out actually that if you follow this definition from complex systems, this couple of very popular clustering algorithms in wireless sensor networks are actually complex in the way we consider it from complex system science. So one thing we did was to basically calculate this complexity, which is again some form of Shannon entropy, if you want, that measures how non-trivial the interactions of the nodes that do a certain function is. So this value CF is that functional complexity. And then we try to see how it correlates with a couple of metrics like energy efficiency and the scalability. So the scalability is defined as the difficulty to join a certain network. So it's essentially how many messages you have to exchange to join a cluster. So a very scalable network would have only one as a value. So it means you only have to send one message and to attach to the network. And a higher value means it's less scalable. You have to exchange more messages before joining the network. Energy efficiency is a ratio actually that tells you basically how much you exchange information locally versus how much you exchange it over larger scale. Because I mean, if you exchange more signals, let's say if you communicate locally, it means you are more energy efficient, right? You spend less energy. So a higher value of this ratio would mean a higher energy efficiency. So now an algorithm like Leech would have a very high value of energy efficiency, but a low value of scalability, because most of the nodes are close by. But to join a cluster, you have to communicate with a lot of nodes. An algorithm like HCC is the opposite. So you basically have to travel long distances to communicate between the nodes. So it's not energy efficient. But to join, you just have to basically attach to a single node. So it's just one message. So it's very scalable. So you have two extremes, in a sense, in terms of energy efficiency and scalability for these two algorithms. And what we notice is that functional complexity correlates positively with scalability and negatively with energy efficiency. So it means it's kind of a proxy to tell you how you should arrange your topology so you get some performance that you like. So that's one actually example of how you can apply ideas from complex systems, in this case from information theory, from entropy theory, and you modify essentially Shannon entropy to achieve that. The second example of, let's say, research we did that deals more with the information in the context of complex systems, it deals with the frequency allocation problem in a wireless network. So here we use what is called a cellular automaton. It's actually a discrete model that consists of a finite lattice of cells. So a cell here can be anything, but in any agent taking some decisions. In our case, it's actually a base station. And the state is what matters. So you basically decide the state of the cell based on what the neighbors do and your former state. So the rules have to be very simple. Again, you can just observe a certain neighborhood. That's kind of the common approach in complex systems. So here you basically have to decide which radio channel to use depending on what the neighbors do. Of course, you want to avoid interference. So the idea is to use a radio channel that is not used or is not used so much by your neighbors. So this fancy, actually colorful picture tells you what happens in three different kinds of systems. So the central one is actually something that relies on self-organization. Again, it's like the cellular automaton approach, where you have these complex agents that just look at their neighbors. They take some decision about the channel allocation. They have a random timer to avoid clashes, but that's it. So it's very simple, the rule. Yet this very simple rule can achieve actually interference-free allocation. So you see no two squares that are close by have the same color. A color here represents a different radio channel. So it means you can basically achieve interference-free, an interference-free allocation just by doing these simple local rules. On the right-hand side, you have what normally operators do. So they basically have a central allocation. You decide for the whole network what to do. Normally, something that involves some kind of template, which you repeat. While on the left side, actually, you have a completely random allocation, where you basically just decide for each cell randomly what radio channel to use. So the right-hand side also achieves interference-free, but you have to collect much more information because you have to optimize across all the network. On the left-hand side, the random basically allocation is very simple because there is no exchange of information or anything like that. But you see, you have a lot of squares that are close by with the same color. That means you have interference, and that's normal. It's actually expected because you are doing things randomly. So these values tell you actually some measure, again, of complexity, similar to the one we did before, slightly different, but again, some measure of some modified Shannon entropy, if you want, across a two-dimensional network. And let's say if you have non-trivial interactions between the entities in a system, again, it's something that is typical of complex systems in nature too. It means nonlinear interaction. So this value of complexity, which we call EC here, is higher than the case where something is completely regular on the right or something completely random on the left. Okay, so and this H value is the Shannon entropy, which basically measures randomness. So of course, it's highest in the case of a random system, 0 in the case of a completely, say, regular system, and it's something in between for a complex system. So that's the second example of a complex system in communication networks, where you have high value of complexity, intermediate value of entropy, and again, via non-trivial local interactions, you can actually achieve a global performance of that suits you. In this case, no interference. So another good thing about complex systems, they're actually robust to changes. So here, for example, we try to see what happens if you flip the channel randomly in one cell. And it's actually not going to be meaningful to compare with a random system, because the random system would not do anything, okay, meaningful. But it's useful to compare with the centralized allocation that kind of represents what operators do today in terms of channel allocation. So in this case, you see we just change randomly a certain channel, and then we see how the system reacts. So the self-organized complex system actually takes less number of changes, needs less number of changes in a certain neighborhood to achieve a convergence to no interference, while the central basically optimizer needs more changes. Another thing we notice is that there are more chances that you cannot actually converge to an interference-free situation if you use a centralized planner as compared to being self-organized. So basically, there are good indications that if you apply a distributed self-organizing approach that kind of resembles complex systems, what they do in nature, it's a good idea, for example, to avoid interference in a cellular network. So that's the second example of work we did that deals with information and tries to get ideas from complex system science to design better networks, or maybe to analyze and understand them better. The second part of the talk deals with the idea of what we call a network in complex system. It's essentially a graph representing, again, the topology of the underlying system. So it doesn't have to be necessarily a communication network, but in our case, of course, that was the use case. And we did actually a couple of investigations about how we can use ideas from network theory in complex systems to actually design or understand better wireless networks. So in this case, we use ideas from statistical mechanics. So basically, you have the POTS model is essentially something that you can use to basically model energy in a spin system in physics. So it means you have spin up and spin down, and if you are aligned, it means something. If you're misaligned, it means something else. For us, it's actually energy here is mapped into interference again. And then you have this equation here at the top, which uses the delta of Kronecker. Okay, it means that basically this delta will be 1 if the two neighboring cells use the same frequency. Okay, and sorry, it's 1 if they use the same frequency. So it means I increase interference, and it's 0 if they use a different frequency, which means I do not increase interference. So we try to basically map the statistical mechanics model into an interference graph problem. Another thing is that we can notice is that there is this idea of degeneracy in statistical mechanics, where basically you have multiple microstates that lead to the same macro state. So for example, for us, a microstate here is the channel allocations, and the macro state is the level of interference. So if you have degeneracy, it means you have multiple channel allocations that lead to the same overall interference. So what we did was to study what happens if you actually model a realistic wireless network based on some realistic deployment data and some realistic simulator. And so what happens in terms of interference. So here you see actually that these curves represent the number of configurations in terms of channel allocations that lead to the same interference. So that, let's say, if you have a higher value of the curve, it means you have more configurations, so it's easier to achieve a certain level of interference. The interference is plotted in a normalized way on the x-axis. And what we show here is that if you increase the number of channels available, radio channels available, of course you can actually find more configurations that can lead to lower interference. So the curves shift to the left and to the top. So to the left means lower interference, and to the top means I have more configurations available to achieve that interference. So of course, having more radio channels is good. Another thing we modeled is, let's say, this topology is actually based on the definition of interference you give, right? It's an interference graph. So this theta value is a percentage. So theta equal to 1 means I declare a cell to be interfered if at least 1% of its users are suffering from interference from the neighbors. And I say, for example, theta is equal to 5% if at least 5% of my users are interfered by the neighbor's cells. Now, increasing theta means you are actually assuming you have a better hardware or better signal processing to deal with interference, maybe better interference cancellation. Okay, so it tells you essentially you can achieve, of course, lower interference if you have better, robustness to that, right? And so you see actually the values of interference on the x-axis for the right hand column are lower because of that. Another interesting thing we observed is that if you plot the cumulative distribution function, or CDF, of the interference, they actually look like a step signal, if you look at it, like very sharp transition, which means actually that if you consider, say, the cumulative distribution function at 10%, so let's say you want basically the probability to have the interference lower than a value to be 0.1, or if you consider, say, the probability of having interference lower than a value to be 0.9, they're very, very close in terms of interference. So it's almost like a very sharp transition here, right? It is a very sharp transition. So it means if you just accept a tiny bit more interference, it means actually you can have many, many more configurations available, right? For example, it could mean I have a slightly better interference cancellation, or I just have a slightly more modest quality of service requirement. That means you could potentially get an explosion in terms of the number of configurations that are available. So that's one first topic in terms of let's say, the topology aspect of complex networks. Another topic we studied is in network computing. So in network computing is an idea where you actually spread the computation tasks across the network. So normally what happens in, say, in the Internet of Things, you collect some information, say, for example, at the orange and green nodes, right? And then this input information is conveyed to a yellow node, which we call normally the sink, right? And the sink will do the processing. For example, it could be you want to measure the temperature and find the maximum in a certain area. So you collect all the measurements from the sensors, and then you let the yellow node figure out things. But this is a problem in the sense that you might overload the sink node. And another problem is also that you normally rely on an optimal path. Okay, you just want the optimal path to get there faster or to consume less energy to convey the measurements. But the problem with this is, if the optimal path fails, you basically lose everything. So the idea here is that you find different paths from the input to the sink, And as long as you comply with a certain constraint, say, for example, you don't exceed a certain delay or you don't consume more than a certain energy, you're good. It might not be always the optimal path, but it is working anyway. And you also you will not overload the sync node, because basically you spread the computation tasks across the communication path. So normally what you do, you collect the information and you just relay it to the sync. But even if these nodes might be simple, okay, the relays, they might actually be able to do some computation. So for example, you might want to compute the maximum, okay, value, the maximum temperature across a certain set of values. So the idea here is that basically you can distribute the task. Okay, you could ask maybe split the data, and then ask a certain sensor to look at the first 10%, another sensor to look at the second 10%, and then everyone would compute the maximum, and then the final comparison between this maxima is done by the yellow node. Just a simple example to say that you can actually have some computations that are not requiring a lot of computational power, so you can get the nodes that normally help you to transfer the information also to do the computation. So this has implications in terms of the probability of successful computation. So normally you would actually do what is indicated here by the blue line. So you find an optimal topology, an optimal path, and you use that. But if that is disrupted, you actually, if any node in this topology fails, you basically cannot get the computation done successfully. While if you have this set of possible paths that maybe comply with a certain delay requirement, you can actually have robustness. Okay, you can actually have redundancy. So you try, if something doesn't work, you can try another one and then another one. So clearly, if you consider that, it's natural to expect the probability of successful computation would increase. The other plot here is about, it's actually color coded so that the hotter colors, like for example, yellow, means the node is more likely to be involved in this, in the job of the network computing. So doing the computation and forwarding the information. So clearly closer to the sync, the nodes are actually going to be more involved. This is also regular topology. So, things are kind of simple. But basically, it tells you which nodes are likely going to be suffering the most from overstress. So if you actually have these yellow nodes that are involved all the time in the computations, they might consume a lot of battery, and they might actually die out, which is a problem because they are actually very important, right? So you might want actually to check on their use and maybe have alternative nodes that can help them. And not rely only on few nodes, because that is dangerous. Again, the idea is not to go necessarily for the optimal set of nodes here, but maybe to enlarge and have alternative nodes that actually can be more robust in the end. So the final, I'm also keeping an eye on time. I think we're doing okay. So the final actually topic I want to touch upon before closing the seminar with some final considerations, the topic of dynamics. So the idea is that things are not static, right? But they change in time. So nodes are added to the network or are removed. They might fail. You might have new links appearing, disappearing. So that is something we have to consider too. So in this case, we try to see how, for example, you can enable self-synchronization in a dense network. And basically, the idea is that you need to agree on a starting time and a starting frequency to communicate, right? That's synchronization. And usually you rely on some master node. Most of the times it's some kind of GPS connection, right? So from the satellite you get the synchronization signal. But there are some situations in modern networks, like for example dense urban or urban canyon scenarios, where you don't necessarily have the visibility of the GPS. So the idea is that now you could think how the nodes can synchronize without that. So in this case, for example, we propose an algorithm that is relying on an idea which is, again, from physics. The idea is the idea of coupled oscillators. So you have these oscillators that are basically entities with some phase, and based on their capability to communicate with each other or not, they can actually synchronize by observing the neighbors. So we try to do something like that and see what happens if you have a wireless network. So the idea is basically you check what interference you, let's say, what nodes you interfere toward, and actually what nodes interfere toward you. So you build this kind of adjacency matrix, so where you have a neighbor if you are interfering to that node, or if that node is interfering to you. It takes more effort to actually build this matrix in terms of the nodes you interfere to, because if you interfere to a node, you have to actually check with that node if that is true. So you basically need some feedback. So that requires more information. So we do that less often. But one thing you can do all the time is to passively listen who is interfering to you, right? Because you just see who does that. So by combining these two information, what we call the outgoing neighbors you interfere toward, and the incoming neighbors that interfere to you, you can build actually an adjacency matrix, which in graph theory simply means a matrix that takes into account who the neighbors, right, are, which node is connected to whom. So that is actually a way we use to update the timing. So basically you check, who are your neighbors, and then you try to reach some consensus in terms of the synchronization. So basically, every node has a certain local timing, and by taking into account this connectivity via this adjacency matrix, you can actually reach some consensus. So it's a consensus reaching problem. So we compared with the literature, actually, and the best example was this paper 15, which is actually a paper from the 2007, in the EuroSIP journal for wireless communication and networks. And basically what they did was just to consider who is interfering to you, but they didn't consider who you might be interfering to. So they had an incomplete, say, vision of the neighborhood. So by just doing actually this more complete, by just adopting this more complete version of the neighborhood, you can actually see that you can reduce the time to synchronize quite a lot. So it's actually very fast to achieve synchronization, even though you just observe what the neighbors do. So you don't have a global synchronization like, based on GPS and stuff like that. So it's again another example how, the philosophy of distributed self-organization that is typical of complex systems can be helpful for our networks. We also studied the problem of robustness, so to define essentially how robust a massive machine type communication network is. So again, a wireless network is a very dynamic system. So, links are good or bad, depending on things like fade-in and interference and so on. There are other failures that are due to hardware or, say, to things like physical damage, energy, drainage, right? So what we try to do is to capture both these phenomena. So the physical phenomena of the wireless channel being a dynamic thing, and also, some dynamics in terms of the hardware and the energy disruption, and basically to capture both of them into a measure of robustness. And what we noticed actually, so why did we do that? First of all, is because most of the works that studied network robustness in our field were focusing on fixed networks, okay, like internet, things like that. But there was no study studying what happens in terms of robustness to a wireless network. So we basically did that, and we have some analysis. And an interesting thing is that increasing the number of nodes seems to actually lead to a better robustness. While if you go back and check the story of self-synchronization, it's actually more difficult to synchronize if you have more nodes, because you have to reach a consensus among a larger number of nodes. So we can actually see a trade-off here between, for example, achieving self-synchronization or achieving robustness. So they don't go hand in hand. So if you actually want higher capability of self-synchronization, you should have a smaller network. But if you want a more robust network, you should have a larger network. So it's a trade-off for communication engineers to figure out. So the last technical topic I want to touch upon before jumping into the conclusions is actually a topic that comes from chaos theory now. So chaos theory is a theory of nonlinear dynamical complex systems. And what physicists studied there was actually, they found that if you can actually increase your, there is a possibility by using reservoir computing, which is a form of recurrent neural networks where you partly train the network, you partly have some connections that are fixed. So it's trying to achieve a good capability to learn, but keeping the complexity low in essence. So you have this reservoir computing, and if you apply that to a chaotic system, you can actually see, according to physicists, that you can extend your horizon prediction in time by 8 times. So now it seems that this result is actually more general, and it doesn't hold only for chaotic systems. So we try to see if we have, a wireless network and we have a similar, capability, what happens? So the idea is what happens if you can increase your prediction window by this recurrent neural network. So what we saw actually is that it has many benefits. For example, you can increase the sum rate in a massive MIMO system. Why? Because you need, essentially, since you can predict more far ahead, you don't need to basically measure this channel quality information and feed it back so often. So you can do it 8 times less often, and that's good in terms of throughput because you spend less of your bandwidth to collect this information. Similar result we found for the computation requirements in a distributed massive MIMO. Again, you basically need to collect less information about the channel because your prediction capability is longer now in time. We also applied it in terms of a multi-hop system. So you basically have to convey a message from A to B, here in the yellow bottom right figure. And you basically cannot, let's say, go all the way from A to B. So you just pass your message to a certain relay node. Now, these relay nodes can move. So you can basically decide to forward the message via a node if that node is going closer to B. If it moves far away from B, then it's not a good idea. But if you see it's going in the right direction, you basically can give your message to that relay node, and then that will get closer to B. It's basically just it's like getting a lift, right? So basically, if the car is going into into the right direction, you might actually want to get a lift to go right in this toward the city you are supposed to go. Now, why is this good in terms? Why is it getting better in terms of better prediction capabilities? Because again, you have more time to decide. You have a longer prediction window, so you can actually choose a better carrier, a better relay node if you have more time to act. Which means you actually see the latency in conveying the message from A to B decreases. So these are actually interesting results that. I think in terms of information, in terms of topology, and in terms of dynamics, they are all in a sense alien to communication networks. So we really took inspiration from studies that are more from physics or things to do more with theoretical computer science, biology, and try to see if we can adapt some of those quantities and ideas and theories to practical problems. And I think by and large we have been successful. So just to conclude, and then I'm happy to engage with you guys in a conversation after the talk. So the idea is we try to merge things like complex systems and telecommunications, and also keeping an eye on the developments of AI to produce networks that are efficient, scalable, robust, and stable. And we also open the door to actually some computing tasks. It's not just about communication anymore. There is also this idea of network computing where you can distribute computation across the network. Just some thoughts about possible challenges. So people talk a lot about AI. I think we really talk about artificial narrow intelligence. So the AI we use today is very specialized about specific tasks. So you can recognize some picture, or you can play chess, but you don't have the general intelligence normally people experience. So it could be that it's still far away because we are not considering the senses, right? Our bodies. So we are just looking at the brain of the machines, but maybe they need also to experience the world like we do with the physical body, and maybe that part of cybernetics has been a bit neglected. Maybe it's time to go back to that. Another issue with AI is that we need a lot of data, right? And sometimes, especially in our field, like in networks, it's not so easy to get operators to give you data, right? Because they have their own business model and they're not happy to share that maybe competitive advantage they have with this data. So what can you do? Well, sometimes basically what you need to predict with machine learning is not completely unknown, we normally rely on physics, right? These are like electromagnetism, or let's say you want to build a communication system predicting the weather, right? So for that, we have a lot of knowledge from physics. So you don't need necessarily a lot of, an infinite amount of data, right? Some of the things that you need to know are already there, encoded into the physical laws. So you might just want to have a hybrid prior. Some is data you collect, but some is also things we know well from physics. And that's what they call physics-informed machine learning. Now, in terms of collective decision-making, it's a bit of the common thread of this presentation. So the idea is that if you want a system that is very scalable and manages very large dynamics, you might want to actually get the nodes to act locally, communicate locally, and then take some collective decisions. That's really what nature teaches us in terms of complex systems. So the final thought is actually about what we normally do as communication engineers, deals with humans, machines, and environment. So in the past, it used to be we were supposed to design systems to communicate, to let humans communicate, right? I make a phone call to somebody. Now, of course, we have also machines that communicate, right? We see the whole story about the Internet of Things and so on. And the environment is whatever is in between a transmitter and the receiver. Now, all of these three dimensions are seeing very big changes actually in the recent years. So in terms of humans, for example, one thing that has emerged is the need to explain to a person what AI does and why it does it. That's the field of explainable AI. I have a bit of work on that. I didn't present it today, though. And then some other work myself and other people in the communication theory community are doing is actually to try to study the meaning of information, the context. So it's not just about raw bits being exchanged, but there is some function, some goal in the communication, which is important for humans. So these two fields are actually picking up. In terms of machines, well, at some point we'll get more powerful artificial intelligence, and another development that is actually not super far ahead in time is quantum computing. So you will have actually computers that can do much more than the current computers, and so we might have actually very big capabilities in terms of the devices coming soon. Finally, in terms of the environment, we were normally, as engineers, we are normally, at least I was trained to consider the channel as a given. It's something that you have to cope with. It's good or bad, and you have to react to that. But nowadays, with the capability of having reflective intelligence surfaces or drones, right, that can be base stations or users, you can actually design the channel you like, in a sense. So the channel is not anymore just a constraint. It becomes like a decision variable in an optimization problem. So a lot of changes are actually contributing to the future landscape of communication engineering. The last thing I want to mention is there are actually very good quotes out there from, for example, Nobel Prizes in physics about the importance of studying complex systems and so on. So I hope I gave you some idea why this could be useful in terms of communication engineering. And the absolute final slide is what Nikola Tesla actually said about 100 years ago. So he kind of foresaw a world where if we have the internet, we have smartphones and so on. And, it's impressive to see that he did that. Basically when maybe the only technology for communication was the telegraph, right? So I think it shows how much ahead of his time Nikola Tesla was. And it's a good reminder to us, not to consider ideas to be, maybe crazy or impractical just because the times are not ready. I think that's the good thing about research. We should actually always be on, searching for new ideas. And no matter how crazy they sound, right, if we have good if we can back them with good work, we should not shy away from, being bold in terms of predicting the future. Okay, that's all I want to say for today. Thanks for your attention, and I'm very happy to discuss with you about this research.
Nicola, thank you. This was great. Actually, I'm not so happy you killed many of my questions and our students' questions.
Oh, sorry about that.
In your last slide,
yeah,
because as I told you in the briefing, students prepare a little bit about the topic, and they asked a lot about AI. So you already killed that one, and
okay. Sorry about that.
So many of the I'm more than happy, because this shows that there is a match about your roadmap that was not anticipated in the abstract, and
Right,
how
right.
students feel about this. Okay. I have some questions, so you can stop sharing, so if
Yeah.
you want, and then we can just, yeah, okay, so that now we can, the stream will be just between us. So more than happy that, thanks again. Now I need to redo, because you also touch quantum, semantic communications, environment. This is one that some of the folks already also touch. So energy efficiency, because we know the autonomous, so our bodies, our systems are built to, if you think the biology is to save energy, right?
Yeah.
Don't, how does this saving energy that is in our in our DNAs, right? How do you see this environmental and saving energy? That's one of the main goals
Right. I think, a bit the story about complex systems, right,
of
is
any biological system. Yeah,
right.
and I mean, I'm putting a complex system as a whole would like to save energy,
Right,
or
right. I think you're right.
individually save energy, and then get into conflict. This because it's sometimes you want more performance, but it's a trade-off. So you need to put more energy. At the same time, you want the system wants to do these trade-offs. Is this dimension of somewhere in this field heating or affecting
Yeah,
the research?
I think it's a very good comment, Christina. I think, first of all, you're right. Nature does things, they don't do it for fun, right? I mean, the natural systems, they try to be efficient. They try to save energy where they can. So if they can use less energy, they do that. Another thing is that, so we should take inspiration definitely from them. Now, in terms of the energy, is not an aspect we consider too much, but it is definitely important. I think it's part of a trade-off. You're right. If you want to be very efficient in terms of energy, you might have to give up performance. Now, what we notice in nature is that they try to do both, right? They try to be not to kill themselves in terms of too much energy consumption, but they still have goals to accomplish, right? So if you think of ants, they want to find food, or birds, they have to travel efficiently to another place, and they do that, for example, being very close, so they reduce the resistance of the air, right? So they have this kind of local rules that they kind of intuitively apply, and so it's a bit the idea, like if you think about like the problem where we had cellular automaton allocating frequencies, you just check what the neighbors do, or if you think of the self-synchronization, again, you check what the neighbors do. So, for example, fireflies, which I think you have in Brazil, right? These insects that emit light. What they do, they basically check what the neighbors do, and then at some point they all flash together. But there is nobody in charge; they just do it distributedly. So I think nature has become very efficient at using as little energy as possible, but achieving very large scale performance. And again, there is no central optimizer, no engineering,
Yes.
right? They just know how to do it. So I think the idea is to try and see if we can learn something. Yes.
I like very much what you said right now, because it resembles to me to the software-defined networking that
Yep.
try to centralize, at least logically, but we know the software-defined networking implementations don't need to be a physical implementations. They
Right.
put abstractions and logical layers. So I like what you put, because Scott Schenker, you mentioned complexity, and if you looked at Scott Schenker's original talks and keynotes, they were about extracting simplicity out of our networks,
Right.
and he mentioned he pointed to our control planes that were They didn't have the layering that are in the data plane. You know, the multiple layers, and in the control plane we don't have these abstractions. And he was very fortunate to say extracting simplicity, and I loved the quotes that you had. So I will add you and suggest you another one by Scott Schenker for the networking community, that extracting simplicity should be a goal of our community, because adding another protocol, another layer, another indirection layer, and building all the protocol stack for it, it's a nice engineering work, but at the end it does not help our community, because it's another layer of complexity, right? Another component of complexity. So that's why I really loved the way you brought this topic, the way you also compared to biology.
One thing actually I learned by looking at these, complex systems, and now we can use it in networks, that the fact that you do something simply, okay, does not mean you cannot achieve complex goals. So in fact, normally the two things go hand in hand. So if you actually are smart and you take, the right local action, you talk with the right neighbors, you just do enough, but you do it right, the things scale up by themselves. So the information propagates in the right way. It's again what nature does very well. About the layers, I agree with you. I think a lot of it is legacy. We have always done the OSI stack and so on. But interestingly enough, I'm not a quantum communication expert. I'm just keeping an eye on that, and I know some very good people in the area. It's very open, the debate, whether they will have a stack or not. They might actually have a stackless architecture even, and it's not decided. There are many open problems. It's a very pioneering technology, but it's interesting to see they're not sure whether they want something like the OSI stack, or maybe just 2 or 3 layers, or maybe no layer at all. So it's maybe more cross-layer all the way. Maybe, I don't know. It's interesting to see how this is a very important actually topic for discussion. What could be the next version of the internet, right? So it's interesting that's one of the main problems they have, how to go about that.
Thanks. Yeah, I totally agree. I think there is the data plane aspects for performance, that the decisions need to be taken at nanoscales for the packet and the values, the fields, the headers. But there is the control plane aspects that is more like a mesh. And if you look at the 5G control plane with the bus, it's a service-based architecture. So it's all-to-all and sharing information, well-defined APIs, semantic APIs, and so forth. So let me touch. I'm browsing through the questions of our students, but as I told you, we'll need to catch up, because I see a lot of good opportunities to collaborate. Here, some concerns. These are the almost always transversing issues considerations, and I know you will guess where I am going to, which are security, privacy, ethics. In this, in what you presented, and I know we have only a couple of minutes to any thoughts. Okay, it's thoughts. It's not really. What are your thoughts on big transversal topics?
These are very good dimensions. Right now, interestingly, as I told you, I did a lecture tour in the US last month, and in one of the tours, actually, the organizer asked me explicitly to give some thoughts about things like ethics and the implications, for society, for industry, of things like AI, quantum. Now, I'm not a native expert in AI, and I'm not a native expert in quantum. I did my best from the angle, right, of a network engineer. I think there is a movement now in AI that is very interested in holding AI accountable for the decision it takes. So they call it explainable AI or trustworthy AI. It has few names, but the idea is that basically you can. So the AI, say normally we mean machine learning, right? It's like a black box, it works, it doesn't work, and that's it. But if it doesn't work, it might have implications. Maybe you applied to give a loan in a bank, and you might discriminate somebody, or you apply machine learning to drive a self-driving car. What if the car injures or kills somebody? Who is responsible, right? So in the end, you shouldn't just trust AI because it's good. You should understand what's going on for two reasons. Maybe one is legal. You want to see what went wrong and investigate, but it could also be to improve. Maybe maybe something is not right, or not exactly meaningful, and you want to know. I think it's always good as engineers to understand what's going on, right? So I think that component in terms of it might be one of the ways in which you address things like ethics, right, in AI. In terms of ethics, say in things like quantum technology. Okay, just to mention another big topic, there is some concern that the people that have access to quantum computers, or whenever they will be available, they will have a huge advantage over the rest of the world. So it means you have a technology that is potentially the equivalent of the atomic bomb in ICT. You can solve problems that we cannot solve, and get to a different level altogether. And then the idea is, shouldn't such a powerful technology be available to everybody? Or should it be, right now it's like big companies like IBM, they're the ones really doing the interesting work. And these people are after profit, right? Now, I don't want to get political, but in the US, we saw how much somebody like Elon Musk played a role in getting Donald Trump elected, right? So, and these guys have an agenda, right? They are about money, about power, and so I think it's a good reminder that technology in itself is not anymore a neutral thing. It can become a very powerful weapon, right? So I think people are looking into quantum with that perspective. Okay, shouldn't it be a bit more democratic? Because right now it's really some major companies, maybe defense in the US, defense in China, and that's about it. So if they get it right, they will get yet more, of a gap compared to the rest of the world. So I think these are very good questions, and I think they should be addressed.
I really liked your message, your thinking, and I was my feeling now as it's a good concluding set of arguments, and also inspiring. I hope all of our attendees will be inspired in some way, hopefully technological also. But for me, one of the outcomes of this, and for the next editions of this seminar series, is I will try to cut even down the technical part, and this just conversation that is inspiring because it touches multidisciplinary experiences and what you just talked about, not entering into politics, but yes, into other multidimensional cross-domain issues, which at the end of the day, they roll the world, right? And they end up.
I agree, Christian. You see, sometimes as scientists, engineers, right, researchers, we tend to think our job is just to do the work. But the problem is somebody else will use the work. So I think we have a responsibility also to keep an eye on how they use the work we do, right? So I think, without getting political, but we have to be politics aware, or at least society aware.
Ethics, responsible, explainable, like you mentioned, explainable AI. This is the big elephant in the room of everyone. Like, okay, how do you explain? And are you going to be accountable for what you did for this? And engineers in other fields like mechanical, electrical, if there's something goes wrong, there are very well-defined legal issues, okay? Yes. And in our field, this is still evolving. With this thought, Nicola, and I really, unfortunately, need to close because our students, 2 p.m. Brazil time, they already have some classes in person, many of them. But as I said, thank you again. There will be follow-up in offline, and all the best and thanks. And for all the students, see you. We'll have just closed sessions in the next weeks to finalize this seminar class, which is a regular one, and all are still invited to join for the next semesters. And Nicola, we'll keep in touch. Keep safe.
Thank you, Christian. And I really enjoyed it. Thanks for your invite and for all the questions. Yeah, take care.
Thank you. Thank you. It was inspiring, and it will help me put more time into this conversation, which is what we get most value of. Not that your contents were not excellent. Thank you.
Thank you. Thank you, everybody. Have a good day.
Bye.